In the previous video, we covered robust regression using the Renczak algorithm. We ended up with having two algorithms. One is linear regression, the other one is robust regression. The issue though is that we don't know how to actually compare the other two and check and see which one is better. So in this lesson, I am going to go through and cover the method or the methodology that you use to actually compare different models. So this is what we call the performance evaluation or regression model. There is a set process that you do go through to actually evaluate the model that you've done. We haven't talked about splitting your training data. This is pretty much the first time that we're actually doing it here. Typically, what you do is that to avoid data snooping, what you do is that you set aside a portion of your data as the test set and keeping the remaining 80% to actually build your model. So let's just say, let me just draw an example here. Let's take, for example, you have a group of data. Okay, so 2, 3, 4. Okay, and then you have 1 and all the way down, and then likewise all the way down. Okay, so what this trains test split does is that it takes, let me just use a different color. Take this portion of the data. Okay, so this could be 80%, and the remaining portion will be 30%. Sorry, 20%. Now, it could also be that you take a slightly different approach. You take 70%, and that leaves the remaining portion 30%. So what's the point of this whole thing? You are using this portion, all right, to actually train your model. You don't want to use your the whole data to actually train your model, because if you use the whole lot and then test it using the same data, basically you're using tarnished data to actually test your model. You're always going to have a perfect model because your model has already seen the actual data itself. Hence, you actually have these what you call holdout set. These are the holdout set that you use to actually test your model because it hasn't seen that data. Now, some people advocate that you do a slightly different approach. You take 60%, okay, to train, and then take another 20% as the holdout set, and then another 20% as your test set. Why do you want to do that? The model building is on this side. Now, the problem is if you actually use this method, meaning 70-30 or 80-20, once you actually test your model on these, you cannot test it anymore because you already allow your model to look at that data. So hence, people advocate that you train it using 60% and then evaluate. This is the evaluation data set, and you might actually go through a few iterations. Typically, you do most of your training here, and then you ended up with, let's just say, 3 models. You test it using that, test all 3, and then whatever's left, the final one that you select, you run your test data with it. So, no, we're not going to save that. All right. Okay, we were here. So this is really the train set test split that is provided by scikit-learn. Is under model selection, and we are going to use the LSTAT, okay, as our predictor, okay, and the median value as our dependent variable, and then we are training with 80% of the data and 20% being our test data. And basically this train test split, which is the library that's imported from scikit-learn, will split the data into 80-20. All right, the 80% will be in your train data under X and Y, and the remaining 20% will be in your test data. We will instantiate our linear regression model, and we fit it into using our X train and Y train. And we'll run our prediction using the train, and we'll run our prediction on the X test. So all of our prediction is run on X train and X test. And now it's really about evaluating the model. There are a couple of ways to do this. We'll look at method one. Method one is using residual analysis. And what we are doing here is we're plotting the X, which is the Y train here, versus the Y train predict minus Y train. The difference between our Y train predict and also our Y train would be the error. Okay, and then we're plotting again the actual test predict versus the test itself. So basically this is the training data and this is the test data, and look at our model and compare how it performed in sample and out of sample. And the rest is just really setting the label legend. Okay, let's plot this out. Now, if you have a normal model, the model that whereby your model explain all the variability of your data, then it will actually normally will not have outliers that looks like this. In this example, we do have outliers here. There seems to be quite a gathering here and also gathering here as well. So there are some data that is not explained by our model. So if you look at the residual analysis, there are certain form of structure, although it doesn't look very linear, but definitely there are some sort of structure in there. A second way of evaluating the performance of your model is to make use of mean square error, sometimes root mean square error, basically taking the mean square error and take a square root of it. Again, the scikit-learn provide a matrix whereby you can import the mean square error and run the actual mean square error itself. And what you can see here is that the model performed better in sample than out sample. So in sample the error is 36.5, out of sample is 46. So the error actually has gone up. Now, if we look at another method of evaluating the performance of your model, it's called coefficient of determination. Now, mean square error is basically the prediction less the actual value itself, and then take the square of all of them and then averaging it. Now, the average value of the sums of square error cost function, this is useful for comparing different regression models, and is really good for fine-tuning your model via grid search or cross validation. Now, coefficient of determination is really 1 minus the sum of square of error divided by the total sum of squares. Right, so let's just run this again. We can import the R square calculation directly from scikit-learn. And if we look at in sample, it's 0.57. The higher the number, the better it is. And when you look at our sample, it's only 0.43. Now, R square has a value of between 0 and 1. So 1 meaning a perfect explanation. 0 means perfectly unable to explain anything. And 0.57 and 0.43 in sample and out sample, it clearly shows that the model explained in sample data well, but it doesn't seem to do too well out of sample. Okay, now it's always good to actually have a reference point. What I mean by reference point is that what we have done so far is applying these three matrix, performance evaluation matrix, on the empirical data and look at the residual. The only issue is that if you haven't seen this before, you don't know what to look out for. Hence, it's always good to actually compare it against a near perfect model and learn from it. So what I'm going to show you is that we're going to show you an old friend. Okay, this old friend you've seen before. It's in the earlier model that we attempted on, which is the IRIS data sets. Technically, we didn't do this. This is not really the Iris data sets, but I did the actual so-called illustration of it within the Iris notebook, Jupyter notebook. So if you look into it or dig out the notebook, and you will be able to see that I've illustrated this method, basically generating a number, calculate the dependent variable, and then plot it out and run a simple linear regression on it. The only slight difference here is that instead of 100 random numbers we generated in the actual scikit-learn notebook, here we're actually generating 1,000. Okay, so just basically have more data. Again, we run the train test split. The slight variation here is that I'm going to keep 70% to train our model because we have more data now, and keeping 30% as our test set. Again, the usual is x train, x test, y train, y test. We're setting the random state equal to 0 so that when you run this, you're going to have the same output or same result. All right, the same process here, being selecting a model and actually fitting the model, and finally run our prediction. So the prediction in the training and also prediction in the test. Okay, now that we've done that, let's plot the residual analysis. I didn't actually type that out here, so residual analysis. Okay, so when you plot that out, and what do you actually observe here? Okay, so having plot that, you can see that there is an overlap of both the training as well as the test data. There are some pretty interesting observations that you can see here. The orange star is the test data, and the blue star is the training data. They are pretty consistent, right? You can see that they are actually pretty much in the same range, and the range is between +3 and -3. Now contrast that to the earlier model that we looked at. What do you see? The actual range is substantially larger, +15 and all the way down to -25, and therein lies the difference. And in terms of behavior, the blue and the orange seems to be very similar, although when you're looking at the test data, it does actually have a little bit more outlier, and the blue dot doesn't seem to have such a extreme data observation that is or outlier. So this is actually a healthy and one that near perfect model should look like. Of course, if it's near completely perfect, then you basically have it in on one line. But don't forget that the actual limit of the residuals that we use is actually quite narrow. Okay, because this is range of 3 to -3, whereas this is substantially larger between -25 and 15. And if we set it to the same scale, then you will see that it is substantially squashed. Just to illustrate the point, I added this line here, setting the limit of the y-axis from 15 to -25, and you notice that it is actually substantially, the variability is actually substantially more narrow when you actually compare to this same range of 15 to -25. Okay, moving on from that, we'll look at the mean square error. So calculating that, you can see that it's 1.03 in sample and 1.03 outside of the sample. It's slightly higher in the test, but they are pretty actually small. It's only 1 point something. So looking at the mean square error within the actual earlier model is 36 and 46. And you can clearly see that there is actually a substantial difference in terms of the scale. It's literally 40 times difference. And the final one is the coefficient of determination. And if you look at this, you can clearly see the difference is very stark here. 98% variability is explained in sample, and again 98% is explained outside of sample, compared to the earlier model where you have only 57 is explained, in sample data is explained, and once it's outside of the sample of 43 it is not. Only 43 is explained. So the difference is really quite stark. Okay, so before we move on to summarize and end this training, I'd like you to try out the model, the earlier model. Okay, so the earlier model being this one here. Okay, now in the so-called performance evaluation, let me just go over there. What we did use is the LSTAT. Okay, that's only one variable out of the 14 potential variable. Okay, so what happens if you actually try all of them? I'd like you to actually try that exercise. Pause the video and try the exercise and see what kind of value are you able to obtain. And don't pick at my answer. I already put my answer there. When you come back, I will explain to you where I hit the answer in the actual code itself. So for now, let's pause and go and try this out. And when you come back, I'll review my answer to you. Welcome back. All right, I'm gonna walk through with you my example. Then the difference here is really, this is where the hidden, I just basically put a hash there and comment that out. So I'm gonna run all of these, and if you look at the residual analysis, it's slightly better, not that much better, although it's slightly less than 15 and 25. There are still some actual variability that's not explained. So let's run the mean square error. Notice that there's actually quite a substantial drop down to 19 and 33 now, compared to 30 and 46 before. So remember, 57, 43, if I run that now, is 77 and 58. So clearly there are still some numbers that's not explained, or some variability that's not explained when we run a linear regression with all of the input variables. So there's obviously some variability that is not explained in our data. Nevertheless, however, it's still an improvement from the using single feature as the explanatory variable. So let's just wrap up. So far, what we have explained in this video is about performance evaluation and the matrices that you use to evaluate performance. There are of course others that yet to be covered, such as mean absolute error. There are a few ways to improve your model construction. We use the train test split. You can also use a stratified shuffle split, meaning shuffle the actual data rather than having a strict cut at the 80% or the 70% mark. You can also perform some feature engineering to improve your model, combining features, adding, dividing, or designing derivative features. We haven't done any data preparation like missing values, what do we do with them, outliers, what do we do with them and how to treat them. We didn't actually deal with categorical features. Yes, we do have binary, but there's no categorical features, so I didn't show you that. We haven't done any data transformation or feature scaling. We're going to show you in the scikit-learn pipeline. Again, we didn't do any fine-tuning such as grid search and randomized search. And the final one is the ensemble methods, which we will look at in future video. So for now, I hope you have found this tutorial useful. I look forward to seeing you in the next video.